All right, welcome back. We're at Unit 2, looking at molecular and ionic compound structures. And so today we're going to look at the structure of solids, in particular ionic compounds, and look at the strength of the ionic bond and how we determine the strength of the bond. So previously, we looked at potential energy diagrams to compare the strength of covalent bonds and explored how the length between the bonds and the number of bonds influences the strength of that bond. Now we are going to take a look at the strength of ionic bonds and what influences them. First, we are going to look at the crystal lattice. This is the 3D structure of atoms arranged in an organized manner inside a crystal. So ionic compounds are arranged in a crystal lattice, and it is a repeating pattern of positive and negative ions. So we see that we have these positive ions, these negative ions, and they create a pattern. So in purple and green over here, this is the traditional picture of sodium chloride, table salt. And we have the positive sodium, which is the small purple atoms, and the negative chlorine. So we can see that we get this kind of cube structure to it, and down here in the picture below is the actual zoomed in picture of salt crystals, of table salt crystals. So they're actually tiny cubes, and you can use magnifying glass and actually look at your salt at home, and you should see these teeny tiny cubes. So that is its crystal structure. Similar over on the right side, we have the ions. This one is involving a polyatomic ion, so a little bit different. We've got one of our ions there, a positive ion, and then this group with the white and the yellow and the red is a polyatomic ion. So those, again, attach together, attract to each other, and we get a different structure. So I pulled up another zoomed in crystal structure of another type of substance. We get these elongated crystals to that one that aren't necessarily cubes. So we can get different crystal structures. What happens is we take the formula unit, so that's a new term here, and it is the simplest ratio of an ionic compound. So when we write ionic compounds, when we write their formulas, we are creating the formula unit. So all of that practice you did leading up to this, you were practicing writing formula units. So what it shows us, like NaCl, there's one sodium for every one chlorine. But when we look at the structure, we have a lot more atoms than that. It comes as a larger crystal with many sodium and chlorine ions. And so we get this repeating pattern of positive and negative. And the formula unit, NaCl, just shows us the ratio of the positive and negative ions. How many sodium do we need for how many chlorine, basically. If we looked at something like MgCl2, magnesium chloride, we have one magnesium for every 2 chlorine. So we would have a different ratio for that crystal structure, right? 2 chlorines for every 1 magnesium. But we would still see that repeating pattern of the positive surrounded by negatives, and then our negative ions surrounded by positives. So we get this repeating positive-negative pattern. To analyze the strength of that crystal lattice and the strength of the attraction between the ions, we need to review Coulomb's law. Coulombic attraction, or Coulomb's law, gives us a basis for attractions between particles. It can be within an atom, where we've looked at before, between our positive nucleus and our negative electrons. We can look at also, though, the attractive forces between particles, so between positive and negative ions, or between molecules, and we're going to look at that later in this unit as well. So attractions always come back to Coulomb's law. And this equation here really simplifies Coulomb's law. It has a much more complex equation, which we don't have to solve, but we need to understand the relationship. So there's 2 things that influence our attraction between our ions in our ionic compound, so between those positive and negative ions. And the first one is the charge. So when we look at the Coulomb's law, as the charge, positive or negative, increases, the force of the attraction increases. So why is that? When we have greater charges, when we have more positives, more negatives, then we're going to get a greater force of attraction because a larger numerator is going to give us a larger answer. All right. Then we can analyze the distance between the charges. As that increases, if we have greater distance between our charges, so that is based on having larger atoms, okay, then greater distance is going to reduce that force of attraction, okay, because larger denominator gives us a smaller answer in that equation. All right, so the first way we can have stronger ionic attraction, stronger attraction between our ionic compounds, is by increasing the charge on the ions. So we're going to compare some elements. You should have a periodic table nearby. It's always a good, handy tool to have. And we can look at the charge on the ions. So sodium is group 1, so it would be positive 1. Chlorine is group 17, so it's going to be a negative 1 charge. Over here, we've got sodium again, and then we've got sulfur. Sulfur is a group 16, so it has a negative 2 charge. So when we have greater charges, so they both have sodium, so that we really don't have to compare the sodium part. We're really comparing the chlorine and the sulfur. Sulfur has a greater negative charge, so therefore it would have a stronger ionic attraction. So Na2S has a stronger attraction. And that's between the ions. So the sodium ion is more attracted, we've got 2 of those, to our sulfur ion with the negative 2 charge than the sodium ion in NaCl is attracted to the negative chlorine. So we have more attraction here because of that negative 2 charge than we have over here with the negative 1 charge. So we can always look at the size of the charge there. In this next one, we're comparing magnesium. They both have a negative 2 charge, positive 2 charge because they're in group 2. And then we've got oxygen, which is in the same group as sulfur, so it's negative 2. And then phosphorus, that's in group 15, it has a negative 3 charge. So again, the Mg2P3, the magnesium phosphide, would have a stronger attraction between the ions because it has greater charges. So if we think of Coulomb's law, the force equals the charge over distance. So the greater the charge, the greater the force of attraction. All right, so those ions are held stronger, and it's harder to pull them apart. The other thing we can look at in terms of the strength of ionic attractions is when the distance between the ions decreases. So if we want a stronger, so we want to increase that strength of attraction, we're going to have the size of the ions decrease. So this is due to the radius of the ions. Smaller ions will be closer together and therefore more attracted, causing greater attraction. So again, our force equals our charge over our distance. If we reduce the distance, we increase the force. Those are opposites of each other. So let's take a look at these. Sodium is the same in both of them in our first example here, but the chlorine and fluorine are different. So we would want to compare the location of chlorine and fluorine on our periodic table. They are in group 17, and they're in different periods of that group. So fluorine is in the second period and chlorine is in the third. So with fluorine being only in the second period, it's going to have a smaller radius, and therefore the distance between the positive sodium and the negative fluorine is going to be smaller. The distance between their nuclei is going to be smaller than the positive sodium and the negative chlorine here, okay? So if this is fluorine and this is chlorine, since fluorine is smaller, we're going to have less distance between the two nuclei, so we're going to have more attraction between sodium and fluorine than we do with sodium and chlorine. So it's a stronger ionic attraction. Let's look at this second one, magnesium and oxygen, calcium and sulfur. So let's compare their location. So first, magnesium and calcium, they are in the same group. Magnesium is above calcium. So that would tell us that magnesium has a smaller ionic radius. And then oxygen and sulfur are both in the same group. Oxygen is above sulfur, so oxygen is going to have a smaller radius. So if we're looking at our positives and negatives versus our positive and negative of so this would be MgO and CaS. Because these are smaller, they would have a greater attraction between those ions because we reduce that radius between the nuclei. Right? So smaller distance between our atoms, larger attraction. So what this attraction influences is what's called lattice energy. Lattice energy is the amount of energy required to completely separate 1 mole, or 6.022 times 10 to the 23rd formula units, of a solid compound into its gaseous ions, and that's our lattice energy. So really, we're taking that crystal lattice, all those little positives and negatives that are all attracted to each other in that 3D structure, and we want to separate all of them into their individual ions. So we would have a mole of that formula unit. So if it was NaCl, we would have a mole of this thing. So that's a mole of sodiums attracted to a mole of chlorines. So that's really what we're measuring with lattice energy. So the stronger the attraction between the ions, the greater the lattice energy. So that's why we were looking at the strength of the attractions. Lattice energy is influenced by those two factors, the charge of the ions and the radius of the ions. Now, there is an order at which to analyze the strength of attraction. We will always look at the charge of the ions first. And then, if they are the same charge, we will compare the size of the ions, the radius. And we do this because charge has a greater effect on lattice energy than the distance between the ions. Charge is much greater influence. So we always start with charge, check the charge. If the charges are different, then we can determine which one has a greater lattice energy. If they are the same, then we will move on to the radius of the ions and see which ones are smaller and therefore have a greater lattice energy. So let's take a look at comparing some compounds and looking at their charge and their distance between the ions. So we've got NaF, NaCl, NaBr, NaI. So those elements, they all have sodium, and then the other element involved is our halogens, fluorine, chlorine, bromine, and iodine from our periodic table group 17. Again, halide ions is what they're called, the halogens. So we can see from this graph, this is a graph of their lattice energy of the sodium halides, and we can see that as we go from one element to the next, that our lattice energy is on a downward or decreasing trend. So why is that? Well, the sodium all have a positive 1 charge, and the halide ions all have a negative 1 charge. So their charges are the same, so charge is not influencing our force of attraction. So again, we always look at charge first, and then if it's the same, we look at distance. Okay, so charge is the same, so we're not going to look at that. Now we can look at the distance between the ions. Fluorine is our smallest atom in that group, right? Fluorine is the smallest atom. Iodine is the largest. So the smaller the distance, the larger the lattice energy, the more energy it takes to separate those ions. So as our ions get larger, our lattice energy gets smaller. That's why we see that decrease in lattice energy. So we can see that relationship there. Let's take a look at some. So we're going to compare these chemicals and see which ones have the greater lattice energy. I'm going to do a couple of them with you, and then I'll have you try a few on your own and we'll check them. So looking at our first one, we've got barium sulfide and strontium sulfide. So the sulfurs are the same. Sulfur is in group 16 and has a -2 charge, so you can always list their charges. And then barium and strontium are both in group 2, so they both have +2 charges. So again, force is charge over distance. We always look at charge first. Well, the charges are the same. So now we're going to look at the size of the ions. Since they both share sulfur, we can ignore the sulfur. We're going to compare barium and strontium. We want the greater lattice energy. So if we want this force of attraction to be greater, we need the distance to be smaller. So barium and strontium are in the same group. And if we look at their location, we've got strontium over barium in group 2. So strontium is smaller in radius, so it will have the greater attraction between those ions. All right, let's try another one. Aluminum is in group 13, it has a +3 charge. Oxygen is in group 16, has a -2 charge. Calcium's in group 2, has a +2, and they share oxygen with a -2. So looking at that, we see that the charges are not the same. Again, greater charge is greater force of attraction. So from there, we can judge that this one, aluminum oxide, would have a greater lattice energy because it has larger charges. Why don't you go ahead and pause and try the next two on your own and then play and we'll check them. All right, so hopefully you had a chance to try these out. It's really important to practice and then check yourself, make sure you're on the right track. So let's look at charges. Beryllium is in group 2, it's going to be +2. Fluorine's in group 17, it's going to be -1. Aluminum's in group 13, +3. Fluorine, again, repeating, so we have a negative charge. So we've got different charges here. Greater charges is going to give us greater lattice energy. We should have gotten aluminum fluoride. All right, our next one, sodium is positive in group 1. Phosphorus and nitrogen are both in group 15 and are -3 charge. So we have the same charges happening. So we have to look at the distance between them. So if we look at that group, we've got nitrogen and then phosphorus. So nitrogen is smaller, so it will have the greater lattice energy. Less distance gives more force of attraction. So how'd you do? Hopefully you were able to do those last two on your own and get them. So why do we care about lattice energy? Well, lattice energy has a big influence on the properties of ionic compounds. So when an ionic compound has a larger lattice energy, it will have certain properties associated with that chemical. Greater lattice energy will give the chemical a higher melting point. So when we have our ionic compounds melt, they actually break their ionic bonds to become a liquid. So when our ions are all lined up, we've got them positives, negatives, positive, negative. When we actually melt it, we are starting to break some of these attractions between them. So if we have a stronger attraction, a stronger bond between the atoms, it's going to require more energy to melt that and to break those bonds. So if we have a greater lattice energy, more energy required to break the bonds, then it's going to also have a higher melting point. The other thing it'll influence is the solubility. Will that chemical dissolve or not, or dissociate? So when ionic compounds dissolve, or actually we call it dissociation, because when ionic compounds dissolve, we are again separating the negative and positive ions from each other. So we are getting rid of those attractions that exist between all those atoms. So they separate into their ions and are surrounded then by water molecules. So our positive ions get surrounded by water, and the negative oxygen on the water attracts to them. We get our little Mickey Mouse waters. And so they get surrounded by these water molecules. And the water kind of works its way between all the ions to separate them. So the stronger the bond between these ions to start with, the less likely they're able to separate. So they would have lower solubility. If the water is not able to kind of pull these ions apart and separate them, then it's not going to actually dissolve. So when we have that strong lattice energy, or that high lattice energy, we're going to have less soluble chemicals. All ionic compounds will dissociate or separate some, okay? But there is a limit to how much will dissolve. And we're going to explore that in our coming units. That's going to be a key thing, is looking at solubility of ionic compounds and which chemicals dissolve and which ones don't. All right, now we're going to take a look at another example and try this out. Oftentimes, they won't ask you to necessarily list things in order of lattice energy. They'll ask you to rank them in terms of a particular property. And this is how the College Board kind of gets at lattice energy without explicitly saying that. So first, if we look at this, it says rank the chemicals from lowest to highest melting point. So we'd want to look at our chemicals and see what kind of chemicals they are. Are they ionic or covalent? So these ones we can see are ionic because they have a metal and a non-metal in each one. So that tells us first that they are ionic. So if we want to look at their lowest to highest melting point, then we have to analyze their lattice energy. All right, that's what's going to influence the melting point. So we want to go low to high, increasing our melting point. So with all lattice energy, we want to look at charge first. So I'm going to assign the charge for each element. We've got lithium in a couple of them. Those are positive because they're in group 1. We've got oxygen is in group 16. It's -2. Fluorine's in group 17. It's -1. We got fluorine over here as well. We've got aluminum in group 13, so +3. Nitrogen in group 17, so -3. In group 15, -3. Whew. And then sodium in group 1, which is positive. So we can see we've got a positive -2, we've got a positive and negative, positive, negative, +3, -3. So we've got some differences in charge. So I always like to start with my charges and get those elements or those compounds placed based on charge first. So our ones that are different are lithium oxide and aluminum nitride. And those have our largest charges. So larger charge is going to have higher melting point, higher lattice energy. So our highest melting point is going to be our greatest lattice energy, aluminum nitride. Then our next one would be the lithium oxide because it has that positive and -2 charge. Now we want to look at our lowest ones. Those would come from our lowest charges, and we have 2 that match in charge. So now we have to look at their radius, the distance between our charges. So what's common is fluorine between each of them. So then we look at the positive charge, lithium and sodium. So our smaller sized ion is going to give us our greater lattice energy. So that would be the lithium fluoride. And then our larger ion would give us our lowest lattice energy, sodium fluoride. So that is our order from lowest to highest melting point based on their lattice energy. And this is how questions might be approached in multiple choice or free response, and have you apply the concept of lattice energy without explicitly saying, look at the lattice energy. They want to test if you understand what influences the melting point of ionic compounds. All right. So that's the end of this set of notes. There's lots of practice on lattice energy and questions on crystal lattice. So try those out. Come to me with questions, and definitely think about how that charge and that distance influences that lattice energy. We always look at charge first and then distance. All right, thanks guys.